Well, it's time. Yeah, it's time to start thermo class. Let's see who we got. We've got a good class. We've got Brian, Alex, Braxton, Ryan, Bryce. Let's see who else we got here. We got Bryce. Yay, Bryce. Good going. And we have Reagan, Nicholas, Mohammed, Dawson, and Nathan. Big class. We got a good class here. We're going to get started here. Let's see. What are we studying now? Let me think here. Oh, we're studying the second law of thermodynamics. That's what we're studying. It's chapter 7. Yeah. Chapter 7. Today's the 5th of November. You do have some homework. I believe this is homework number 22. Yeah. Let me write that down. Homework number 22. And it's chapter 7, number 15 and number 56. We're going to be studying chapter 7. And your exam is the 12th. Now, when is the 12th? Don't know. That's a week from today, isn't it? Yeah, see, this is the 5th. Your exam, you'll have it available to you on the 12th, which is a week from today. It will be Thursday. And it'll be due that Sunday at midnight. And it's on chapters, I believe it's 5, 6, and 7. Does that sound right? Yeah, that's it. And it's due Sunday the 15th. Okay, we got that figured out. Well, gee, your test is going to be on chapter 7, and we haven't even started on chapter 7. Maybe we better get started. That's a good idea. But before we do, did any of you have a comment or question about anything? Comment or question about anything? Well, okay, let's get started then. Now we did the second law for control masses. And the way that goes is if you have a control mass, the second law can be written like this. Now this is called the heat transfer term of the second law. And this is the generated entropy term. Now you can do everything in little letters if you want. That'd be okay. We just got them in little letters, which means per mass. See, this would be the change in entropy per mass, or you could say the change in specific entropy. And this would be the heat transfer per mass divided by the temperature of your boundary through which that heat transfer takes place. See, heat transfer always takes place at a boundary. Like if you're shaking hands with somebody that has a cold hand, your hand and your friend's hand, you clasp them together. That's the boundary. The boundary is the boundary between the two hands. And the heat transfer always occurs from the warmer hand to the colder hand. But it's got to be in Kelvin or Rankine. That temperature must be an absolute. And this is the entropy per mass, entropy generation per mass. And you remember the rules on that. If this is 0, you have a reversible process. If it's bigger than 0, you have an irreversible process. If it's less than 0, you have an impossible process because you have violated the second law of thermodynamics. Okay, but see, that's for control masses. That's not what chapter 7 is about. Chapter 7 is about the second law for control volumes. What they did was they just divided this through by time. If you divide this through by time and make that time approach 0, make the time very short, that's really the definition of a derivative. So the second law for controlled volumes is the derivative with respect to time. See, if you divide that by time and make the time approach 0, that's what a derivative is. And see, this turns out to be equal to the sum of your Q we'll do it in big letters. The sum of big Q dot over T plus big S generated. But see, if you have mass coming in and mass going out, mass has entropy. Entropy is a property just like temperature and pressure and volume and all these other properties, and enthalpy, and even mass itself. And so what you have is an incoming transfer of entropy given by m dot little s, and an exiting transfer of entropy with respect to time given by m dot little se. Now you'll find that equation someplace in your book. Let me see if I can find it. That's your second law for control volume. I need chapter 7 is what I need. Yeah, whoops. Okay, let me keep looking here. Probably is at the end of the chapter. There it is. I see it. It's on page 206. Page 206. Yeah, there you go. Now they've kind of switched things. They put these terms here first, and they put a summation sign on these. And on this one here, they put a summation sign. See, if there's more than one incoming, you might have more than one entrance into your system. Then you need to sum them up. And you might have more than one exit to your system. So you have to sum them up. But if you just have one entrance and one exit, you don't need the summation. But there you have it. I see that equation. We just did it. All right, great. And then they have a lot of examples. We could do some of these, but you could read these yourself. You don't need me to do these. We might do some anyway, though. They have 2 nozzle problems and a compressor problem. And you guys could do those. That would be wonderful. Then they have a transient problem. I don't know if we'll do that today or not. But let's do some problems using this second law that we've just talked to you about. So there's your theory. There's your homework, and there's your test coming up next week. Any questions before we do some example problems? Well, okay. I wanted to do problem 718. So we'll just work on problems now. That'd be good for us. I'm going to erase all this stuff because I need the room. And on 718, let me find it. You know the drill. We draw a device sketch. I'm trying to find 718. I found it. It's nitrogen gas. Now, nitrogen gas is a diatomic molecule like that. It's flowing in a pipe at 500 kilopascals, 200 Celsius. They give the velocity. And it goes into a nozzle. So basically, you got a pipe here. And then it's connected to a nozzle. There you go. And in comes this nitrogen gas at 500 kilopascals, 200 C, a velocity of 10 meters a second. And it comes out at 300 meters per second. Well, that's what nozzles do. This is your pipe, and it's connected to a nozzle. And what nozzles do is they speed up. That's why we have nozzles. Notice that it went from 10 meters per second to 300 meters per second. Wow, it really got fast. I don't know if you've ever used a paint spray gun, but they have a nozzle on that. And when you pull the trigger on your paint spray gun, it comes out very fast. And those things can be dangerous. You want to be careful with that paint spray gun. Let's say you had some green paint and you're painting the side of a wall there with this green paint, and you get careless and you bring that nozzle a little too close to your leg or your arm, for instance. You will inject some green paint into your leg or arm, and it's going to be pretty ugly. You don't want a big glob of green paint injected into your leg or arm, do you? Nozzles really speed up. Okay, now let me keep reading. If you just tuned in now, we're doing problem 718. Now they want to know the exit pressure. Well, let me write that down. This is the exit pressure. And they want to know the area of the exiting area here. See, this area here is what they want to know. What's the area of that exit? All right, and they said the mass flow rate. They told us that. Let's write that down. The mass flow rate is 0.15 kilograms per second. The expansion is reversible and adiabatic. Okay, well, we'll write that down. But now here's something. The mass flow rate is constant. You don't want mass building up in this thing. It would blow up eventually. So whatever goes in in a given amount of time has to come out in that same given amount of time. So the mass flow rate is constant. 0.15 going in, 0.15 kilograms per second going out. All right, we know that. Now for the first and second laws. Let's write those. Well, we know this by heart. The first law, we've done nozzles before. I won't start from Genesis here. I'll just give you the first law for nozzles. It goes like this. You all knew that. That's the first law for nozzles. And we're going to do a little algebra on this now. We're going to write it like this. Make sure I did my algebra right here. Can you get to there? Can you get from here to there? I bet you can. And then, you know what this is? Let's see, probably a creditor. I just push the green thing and then I push the red thing. That works. Okay, you know what this is? You could write this as C sub P delta T, because that's the change in specific enthalpy. We got a nice equation for it. Let's look it up. What is C sub P for nitrogen gas? Go to the back and help me shop around here. Nitrogen gas. I found it. It's 1.042. It's 1.042 kilojoules per kilogram Kelvin. And make sure I got that right. That's table A5. Go to the back and look that up for me. Make sure I got that right. Nitrogen. Yeah, that looks pretty darn good. I like it. Okay, now the change in temperature. Uh-oh. We don't know the change in temperature. The final temperature, we don't know. The initial temperature, we do. The initial temperature is 200 C. Might need Kelvin there. I don't know. Well, I'll put C here for right now. There we go. But you know what? We do know what these are. And we could do this equation and get the final temperature. You like it? I kind of like it. Here, let's put the numbers in. Now this is 10 meters a second squared over 2 minus 300 meters a second squared over 2. And on the right, we have 1.042 kilojoules per kilogram Kelvin, T2 minus 200. We'll keep it in Celsius. I don't think it matters here. Now here's the problem. A meter squared per second squared, I don't know if I've shown you this before, but you know what that's equal to? That's equal to a joule per kilogram. But see over here, what we're going to have is a kilojoule per kilogram. Probably ought to put that in Kelvin. Let's do it. 200 plus 273.15. Let's put this in Kelvin. We'll all feel better about it. It'll be 473.15 Kelvin. See, over here, we're going to have kilojoules per kilogram. But over here, we got joules per kilogram. So you have to do this little trick here. You have to multiply all that stuff by a kilo over 1,000. That'll give you kilojoules per kilogram. This will give you kilojoules per kilogram because the kelvins will cancel. And what we're going to do is we're going to take our calculators. We're going to plug in all these numbers. Well, you're going to have to divide by 1,000 over here. And then we're going to solve for T2. Now I'm going to shut up. You guys have a minute and a half. I want you to plug all that stuff in and find T2. I'll be quiet. We're going to get the exiting temperature. Now it's going to be colder. Nozzles make things colder. Well, I got the exiting temperature. Did anybody get 430 Kelvin on the exiting temperature?
Uh-huh.
Good. Now you see the incoming temperature was 473 Kelvin. And we cooled off quite a bit, really. What is that, about 43 degrees? That's quite a temperature drop, isn't it? 43 degrees. Nozzles will cool you off. Okay, well, we got our final temperature. So what? Well, what are we supposed to find here? Just a minute. Let me read this. Determine we need the exiting pressure. Huh. Exiting pressure. Well, I need some room. Is it okay to, I need some room someplace. How about I erase all this stuff? Here we go. I'm going to erase all this stuff so that I can. Tell you what, let's write the second law. Now we've written the first law. You know what we haven't done? We haven't done the PV diagram or the TS diagram, have we? And we haven't written the second law. But we made a little progress. We've got the exiting temperature. It's 430 Kelvin. Well, here let's do the PV diagram. Now it's true that nitrogen can be liquefied. Have you ever heard of liquid nitrogen? Go down the freeway sometime, a big truck goes by, says on there liquid nitrogen. Yeah, they have liquid nitrogen, you bet. So it does have a vapor dome, but I think we're way out here in the superheated vapor region is what we are. And I think we can treat, I mean, it's 200 Celsius. It's kind of on the hot side, isn't it? I think we can treat this as a ideal gas. But we could look, they do have a nitrogen table. We could look at that. That'd be fun. But let's see, we got 500, well, tell you what, let's just look at the nitrogen table. Go to the back and shop with me. We're looking for nitrogen. Don't see it. Aha, I see it. Nitrogen. There is a nitrogen table. Okay. Now it goes up to 126K and something 3,000 something kilopascals. Here, let me write that for you. This thing peaks out at 33 and 97.8 kilopascals. I am on table B6 in the back of your book. We are not going to be in that vapor dome, but I'm just showing you there is a vapor dome. Nitrogen can be liquefied. Now the temperature is a 126.2. They call that the critical temperature. 126.2 Kelvin. What are we? Well, my gosh, we're 473 Kelvin, aren't we? See, we're way the heck out here. We're at 473 Kelvin. We're nowhere near the vapor dome. And we're going to 430 Kelvin. Well, that's in between these two. Here, we'll draw it. There you go. That's your 430 Kelvin. And what about the temperature? Yeah, well, that is the temperature. It got colder. What about the pressure? We still don't have it, do we? But if you looked at the second law, we'll write the second law in a minute, but let's go ahead and get that pressure. See, here, let's do the TS diagram first. There we go. TS diagram. There is a vapor dome, yeah. But where are we? Well, we're way the heck up here. We're at 473 and 430 Kelvin. And our process is going to go straight down from 1 to 2. And here we're going to go from 1 to 2 like this. Now, why is it straight down? Well, it's straight down because the second law says there's your second law. And this term here is 0 because this is a steady state nozzle. Nothing is changing. None of the properties change with time. It's steady state. This is 0 because if you read the problem, we're doing 718. It says here, it's reversible and adiabatic. Did you see that word adiabatic? If it's adiabatic, that means there's no heat transfer. There's no heat transfer rate. And this term here is 0 because, because it's reversible. If you read the problem, it says it's reversible. That means that the entropy generation rate is 0. It's reversible. Now the m dot is the same for incoming and exiting. So you could do a little algebra here and go m dot si minus se. Well, something's got to be 0, and it's not m dot because m dot is 0.15. That's not 0. So this term here has to be 0. The incoming and the exiting specific entropy have to be the same from the second law. You can see it. Now we have a nice name for that. You see what this amounts to is the change in entropy, or entropy per mass, or specific entropy is 0. If your change in specific entropy is 0, we have a special name for that. Let me go to one of my excellent students. Reagan, I'm always picking on Reagan because he's a good sport. Reagan, unmute and say hi.
Hi.
Yeah, hey, Reagan, what's the special name for a process where the change in specific entropy is 0? What's the name of that?
Well, I can hear you very good. Can you please repeat?
Let me say it again. We have a special name for the process when the change in entropy is 0. What's the name of that process?
Is that a diabetic process?
No. Here, let me write it down for you. I need some room. How about this room right? We don't need that stuff anymore. If delta S is 0, they have a special name for it. It's called an isentrope. Reagan, do you remember that? Do you remember that name, isentrope?
Yes, I do.
Yeah. And I think I showed you last time, if you have an isentrope and you can treat it like an ideal gas, I think I showed you this equation. Reagan, do you remember that equation?
Yes, I do.
Yay! We can use it here because we have an isentrope and we have an ideal gas. Now let's circle the stuff we know. Do we know T1 and T2? Yeah. T1 is 473, T2 is 430. We know those. Do we know P1? Yeah, P1 is 500. We don't know P2, but we can find it. We're going to find it. But we need to look up this K thing. Now that K thing has a name. I bet there's not a single student that knows that name, but we're going to try Taylor. Taylor, unmute and say hello, please, Taylor. Earth calling Taylor. Come in, Taylor. Uh-oh, coffee break. Nicholas Sabrata, unmute and say hello, please, Nicholas. Earth calling Nicholas.
Hello.
Hey, there he is. Nicholas, there's this thing called K. I tell you what it is. It's the ratio of C sub P to C sub V, and it has a name. Do you know the name of that, Nicholas?
I do not, sir. I'm sorry.
You're going to learn it. I'm going to tell you what it is. It's called the specific heat ratio. I'll write it for you. Specific heat ratio, and it's given in the back of your book. Now go to the back and let's look up K for nitrogen. Go to the back and start shopping around and look on table.
A5, I got 1.4 for nitrogen.
Yes, good going. It's table F4, isn't it? Did you find it on A5? Is that what you said?
Yes.
Okay, let me find A5. I think I was looking in the English table, but it's the same. This particular thing is the same whether it's metric or English. And A5, I'm having trouble finding it. Okay, here we go. A3, A4, A5. Good going. It's nitrogen. It is 1.4. Good going. For nitrogen, it's 1.4. Well, let's write the numbers. We got some room down here. I think maybe we have enough room right here. T2, we know, is 430. T1 is 473 equals, I didn't need parentheses there, equals T2, no, P2. We don't know P2, but we're going to find it. P1 is 500. 1.4 minus 1 over 1.4. Okay, we have an equation now, and we can solve for P2. I'm going to shut up here for 1 minute, and I want you to solve for P2. Go ahead. There's our equation. I just plugged in the numbers. We should be able to solve it. Well, I got my P2. I got 358 kilopascals. Did anybody get that? If they did, say, uh-huh.
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 Yeah, that's 3 of us. I want one more uh-huh.
Uh-huh.
I bet that's right. So we just solved for P2. What else are we supposed to do? Let me read this. Determine the exit pressure. We did that. We got it. And now find the cross-sectional area of the nozzle. Let me check with the answer book and see if we got that pressure right. Well, I got 357.4. That's dang close to 358. I'm happy with it. I must have rounded off. So we've got the exiting pressure, but they want this area. Okay, well, let's see if we can get the area. Now I need some room here. And by the way, I really think this pressure goes quite a bit lower. See, at the top of the vapor dome, it's 3397, and we're going all the way down to 358. So what we're doing is this here. It's more like that. We're going to a lower pressure. That makes sense. There's your state 2. It's much lower. And here's your pressures. The way the pressures work is the 473 the pressure coming in is 500. Well, I'll fake it here. There's your 500 kilopascals. And here's your, what do we say it was? 358, 358. It's down here someplace. There's your 358 kilopascals. And it goes straight down from 1 to 2, it goes straight down because the change in entropy is 0. So there's your TS and PV diagrams. There's your device sketch, but we haven't got the area yet. So I need some room here. Let me make some room and we'll find the area. You see the area of this nozzle here? They want us to find the area. Okay, well, here's this equation here. Now that equation is good for inlet or exit, but we're really interested in the exit. That's what they want. They want the exit area. That's what this is, the exit area. Now we know the mass flow rate. That's given someplace. There it is. It's 0.15 kilograms per second. We know that. We know the velocity, don't we? Yeah. What did they say the velocity was? 300. The exiting velocity is given. It's 300 meters a second. Okay. So we know what that is. You know what? If we could get this exiting specific volume, we could find the area of this nozzle, this exiting area. Now, how would we get the specific volume? How about this? PEVE is equal to RTE. Now, do we know PE? Yeah, we just did it. It's, let me write it down here. It's 358 kilopascals. Uh-oh, we got to look up the gas constant for nitrogen. Go to the back and shop with me and find the gas constant for nitrogen. And it is I'm getting 0.2968. 0.2968 kilojoules per kilogram Kelvin. Exit temperature, we got that. Oh, gee, did I erase it? No, there it is. It's 430 K. Okay, look at here. We got a nice equation with only one unknown, and we can solve for it. And then once you get that, we can get the exiting area. I'm going to shut up for a minute and a half. I want you to find the exiting specific volume. And then once you find that, plug it in here, and then find the exiting area. Go for it. Well, let me call on somebody. Let me call on somebody. I've already picked on Taylor and Reagan and Nicholas. Nathan, I haven't picked on you yet. Nathan, unmute and say hello, please.
Hello, would you like the area?
Yeah, go ahead. Give me the area.
Okay, it is 0.000178 meters squared.
That's what I got. That's what I got. But now where's room enough to write it is my problem. My big problem is I don't have any room here. We'll sacrifice that. But first of all, I'm going to write the specific volume. I got 0.357, and you must have 2. I'm talking to Nathan, right? Yeah,
Yes, I got that.
yeah. And what that is cubic meters per kilogram. And then the area, the exiting area, you have to plug that there. Once you know what that is, then you can find the exiting area. And I got what Nathan got, 0.00017. I can't read my own writing. It looks like an 8. 178 times 10 to the minus 4th meters squared. Let's get that.
That is
square.
already with the -4. So there's no 10 on that.
Oh. Honk and thank you point. That's already got the -4. You're absolutely right. And I was absolutely wrong. I'm curious to see how big that is. I want to draw a exact drawing of that. I'll tell you how we could do that. I know what a square centimeter looks like. Here, I'll show you what a square centimeter looks like. I've got some centimeters here, and they're not very big. That I don't know if this even shows up, guys. That's supposed to be a square. Can you guys see that little tiny, supposed to be a square? That's a square centimeter. Let's find out how many square centimeters this is. Now, the way to do that is to do this. Go 100 centimeters is a meter, and then square it. And see, you'll get rid of your square meters, and you'll get square centimeters. Here goes. This is what 1 square centimeter looks like. And we're going to do that. Here we go. 0.000178 times 100 squared. You know what I get? I get 1.78 square centimeters. So, you know, that's a little bigger than 1. Not much. Not much. We're talking about maybe a little bigger. What do you think? I'm just faking it here. But it's big. It's bigger. That's the nozzle exiting area, 1.78 square centimeters. Okay, well, that was fun. Now let's do another one. Was there any question on that one? Okay, we're going to do another one. I'm going to erase all this stuff here. Did I give Nathan his thank you point for what he just helped me with, or is that somebody else's? I lose track of thank you points. Nathan, did I put your thank you point on the board?
You did. Thank you very much.
Yeah. Thank you very much. You're helping the class when you do that. Okay, now this next one is I think the more problems we can do, the better. Now this one is a compressor. This is 722. Let's do that together. And then be reading your chapter, because Tuesday, we'll continue learning other stuff in our chapter. But let me find this 722. I believe it's a compressor. Here we go. 722, a compressor with air. It's got air in it. Okay, well, let's draw the device sketch. You know, compressors kind of look like this here. And they have mass coming in and mass going out. Do they tell you what the mass flow rate is? We're doing 722. They don't tell you. But they do tell you that it's air. That's nice to know. And you know, if it's a compressor, you have to input power. Only I don't think they want power. They want the specific work. They want little w. See, little w, you all know that this here stands for power. This stands for work. This little w stands for work per mass. And a little w dot would stand for power per mass. We need to be familiar with the units. See, power would be, in this case, are we in English, senor, or are we in metric? Let's look and see. It looks like metric, Kelvin, kilopascals. Well, then this would be in the watts, or maybe kilowatts. I don't know. Probably kilowatts, unless it's a very small compressor. And then it could be in watts. Now the work is going to be in kilojoules, or maybe joules, depending if it's a very small compressor, but probably kilojoules. Work per mass, what's that? Well, that's kilojoules per kilogram. We got to know this. We got to know what these units are. And this would be kilowatts per kilogram. So there you have it. There's your units. And they want this. They don't want this other stuff. They want the little w. Okay. Now let's label all this. We got air. We're coming in at 300K. 300K, 100 kilopascals. Then what? Then the pressure coming out is 1,000 kilopascals. Pressure went up. Well, that's what compressors do. They increase the pressure. We went from 100 to 1,000. Now they said it's a reversible process. We're going to assume, because it's a compressor, that it's adiabatic. Compressors are basically adiabatic. So we can assume that. They want to know how hot is the exit flow. They want to know what the temperature is, and the exit temperature, and they want to know what the work per mass is. Okay. Well, there's your device sketch. We just did the device sketch for problem 722. Now what's next? Probably the PV diagrams. Let's do that. There's going to be a PV diagram and a TS diagram. Hey, do both. For a while now, you do both for me to keep me happy. I want you to know how to do both. Okay, on the PV diagram. And well, let's see, you're coming in at 300. Did you know it's going to get hotter? Compressors make it hotter. So I don't know what T2 is, but we're going to find out. Here's your 300 degree Kelvin isotherm. There it is. Now, I don't know what the exiting temperature is, but it's going to be hotter. And isotherms go like that. We'll just call it T2 for now. That's a nice name, T2. And it's an adiabat. You know what adiabats do? They're steeper than isotherms. It's going to do something like this. It's going to go from 1 to 2. Have I ever told you that adiabats are steeper than isotherms? I know I've told you that about 6 times. Now this pressure here is 100 kilopascals, and this pressure here is 1,000 kilopascals. So there's your PV diagram. Now let's see what the TS diagram. Notice there's no vapor dome. We're not going to liquefy. This is air at those kind of temperatures. Are you kidding? Okay, let's do this one now. Here's your T2. We don't know what T2 is yet, but we will in a minute. And here's T1, which is 300K. Now, for ideal gases, the isobars go like this. There's your 100 kilopascal isobar. Now, because this is a reversible adiabat, they said it's reversible, and we know compressors are basically adiabatic. Then we have an isentrope. Remember, I asked one of my students that. And do you know what an isentrope is? Well, it's when delta S is 0. There's no change in your entropy. So we're just going to go straight up. There you go. There's state 1. There's state 2. We're going to go straight up. It's an isentrope. And we're lucky. It's an ideal gas. You have air, so you get to use this lovely equation again. Now be careful of this equation. You don't always get to use it. When can you use it? You can use it for an isentropic ideal gas. What if you have maybe a refrigerant? You can't use it. What do you do then? You use the tables. You go to the back of the book and you look up stuff in the tables. Did you know they have values for specific entropy in the tables? You look them up. That's how you do it. Okay, now let's put in our numbers. Here we go. T2 is, we don't know. T1 is 300. P2, we do know it's 1,000. P1 is 100. And you look up K for air. Now, you remember what K is. K is the ratio of C sub P to C sub V. It's got a name. It's called the specific heat ratio. See, air is 1004 and 0.717. And if you'll do that, you'll get 1.4. So we know what this is. It's 1.4 minus 1 all over 1.4. I'm going to shut up. I want you to find T2. Find T2 for me. Well, I got an answer for T2. Let me go to one of my excellent students here. Let's see. How about my friend Mohammed? Unmute and say hello, Mohammed.
Hello, sir.
Yeah, hello. Hey, Mohammed, did you get the exiting temperature on this compressor?
Yes, sir. I got 579.20.
That's what I got. 579.2 degrees Kelvin. Here, we can write it down here. It's 579.2 Kelvin. Got hotter, didn't it? Started off at 300 and went up to 579.2. That's a big increase, but that's what compressors do. They get hot. They get hot. And we are lying to you a little bit because they get hot. They do radiate some heat out into the environment, and the Q is not strictly zero on a compressor, but it's close. It's close. And so we can get away with this. We can assume it's adiabatic, but there is some heat transfer. So I don't know, we're lying to you a little bit. Okay, well, we got that. Now, what are we supposed to do? Let me read the problem. I got lost here. We're doing 722. And it says here, how hot is the exiting flow? Well, we did that. And what is the specific work input? Oh, we haven't done that yet. We haven't found this work per mass yet. Well, how would we do that? The first law. We're going to use the first law. Let me write that. Make some room here. We don't need all this stuff anymore. We don't need that. We got plenty of room here. We're going to write the first law. Now, this is a compressor. And the first law looks like this. We just have one inlet and one exit, and the mass flow rates are the same going in and going out. And the rate of change of the total energy in our compressor with respect to time is 0, because the properties don't vary with time. Now they do, the properties vary with location. Look, the temperature varies. It goes in at 300 and comes out at 1,000. The pressure varies. It goes in, no, the temperature goes in at 300 and comes out at 579. This exiting temperature is 579 Kelvin. And the pressure varies. It goes in at 100 and comes out at 1,000. The properties do vary with location, but not with time. An hour later, the exiting temperature is still 579. So this is 0. They call it steady state. This is 0. We're assuming this compressor is adiabatic. Here, I'm going to pull a little sneaky trick. I'm going to divide everything in here by m dot. And if you do that, you can just write this as a little w. And we can get rid of the m dots. And oh, we got a nice little equation. You see what I did? I divided through by your mass flow rate. So here we go. The work per mass is going to be HI minus HE. You know what that is? That's the negative of delta H. Because delta H is HE minus HI. Okay, and you know what that is? That's C sub P delta T. Now we know what the temperatures are, and we know what C sub P is for air. It's 1004 kilojoules per kilogram Kelvin times T2, which is 579.2 K minus T1, which is 300 K. Go ahead, put that in your calculators and get the little W for me, please. I'll be quiet for a minute. Right now, we're finding the work per mass done by this compressor. Well, let me find one of my very best students here. How about, I don't think I've called on Bryce. Bryce, I haven't called on you, I don't think, have I?
No, you have not.
Bryce, did you
Yes.
figure out this work per mass for this compressor?
Yes,
What'd you get?
I got a it's negative 280.3 kilojoules per kilogram.
That's exactly what I got. It's exactly what I got. Now it's negative. That's what compressors do. They do negative work. What does that mean? It means you got to plug them in, see? This thing is connected to a plug someplace. Did you know your refrigerator has a compressor? And you have to plug that into the wall socket there, or else that compressor doesn't work. It requires an input of power to run the compressor. I think I've told you this before. Compression work is negative, expansion work is positive. And you did great. And we got that under our belts. Now let me give you a preview of what we'll be doing next week. Today's Thursday. And next week, here's what we'll be doing. But first, is there any comments, any questions on anything? You should be getting the pattern by now. Device sketch, PV diagram, TS diagram, first law. Now, we didn't write the second law, but it turned out that the change in entropy was 0 because it was an isentrope. And that helped us. See, that just goes straight up. And you get to use this equation. So that's the pattern. Okay, well, let me make some room, and I'm going to tell you what we're going to do next week. Unless you have a question, here's your last chance. I'm going to erase this stuff. Okay. Now, next week, we're going to talk about device efficiency. We've talked about efficiency before. We've talked about efficiency before. But always before, we talked about it in terms of a cycle. Like, for instance, a power cycle. a power cycle has a clockwise schematic. It has a hot temperature, a lower temperature, and it provides you with power. That's the schematic for a power cycle, and it has an efficiency. And we studied that. In fact, the equation for it was eta equals W dot divided by the heat transfer rate at the higher temperature. See, there's your QH dot. This here is QL dot. And those equations are in your textbook there someplace. But that's the efficiency. It's always something you desire divided by something that costs you. That QH dot costs you money. You got to go buy fuel, okay? It might be gasoline, it might be coal, who knows what it is, but it's something that it's going to cost you time, effort, money. But see, that's the efficiency of a cycle. Well, what we're going to study next week, coming attractions here, and I want you to read about it, and we'll study it next week, is the efficiency of devices. See, some devices are more efficient than others. Like, for example, turbines. There's efficient turbines, and there's turbines that are inefficient. Let me see if I can find where that is. Here it is. The efficiency of a turbine. When you go and buy a turbine, probably the expensive ones are more efficient than the cheaper ones. Does that make sense? Kind of does. But what the efficiency is of the turbine is the work that you actually get. Well, I'm doing work per mass. The work per mass that you actually get divided by the work that you would get if the turbine ran perfectly, which that would be a reversible process. See, if it's a reversible process, well, there's no bad things happening like friction, for example. See, friction, that robs you of your efficiency. That's why your automobile has oil. One of the reasons, it's also to cool it. But the oil reduces friction, which you want. Because the more friction you have, the less efficient your automobile is. There's all kinds of friction. There's friction with your belts. You got belts inside your motor there. They have friction. You got bearings. They have friction. But this is the definition of the efficiency for a turbine. You'll discover that this actual work per mass is always less than the maximum possible, which is the reversible work per mass. That makes sense. The actual is always going to be less than your maximum. You could call that maximum if you wanted to, but it turns out to be the reversible. Now that's for a turbine. Now let's talk about a compressor for a minute. For a compressor, they have efficiency too, but it's just the opposite. They've got the reversible in the numerator and the actual in the numerator or in the denominator. Because see, in a compressor, you have to input work. And the less you put in, the better. Does that make sense? This is always going to be less than 1 also. But if you can make this actual work that you're inputting smaller, you've got a better compressor. Costs you less money. Remember, you have to plug in the compressor. You have to pay for the electricity at the end of the month, or your landlord does. And you want to pay a smaller amount. You want to have to input a smaller amount. It's just sort of the opposite, isn't it, for a compressor? Well, that's probably all we'll have time for. There are those two, but all devices have efficiencies, but we'll be lucky to cover those. Is there any last comments or questions? Well, I hope you had a fun time. I always do. Let's adjourn, and I will see you guys Tuesday at 11 o'clock, right? See you then. Bye-bye, students.
See ya, bye.
All right, thank
Adios. Adios, muchachos. See you then.